Welcome to the lecture 50. In this lecture, I will discuss about Noetherian modules, Artinian modules, Noetherian and Artinian rings. So, let me start. Noetherian rings, Noetherian modules, and also previous lectures also we have seen Artinian modules and Artinian rings. So, one remark I want to start that every submodule, in fact every Noetherian module is finitely generated. Why? Because module itself is a submodule, therefore it is finitely generated. But whereas an Artinian module need not be finitely generated. Okay. So, let us see an example. So, let p greater than 0, this be a prime number, okay, it is a prime number of course in Z. For n belongs to natural number, G p power n is denotes the set of all p power n roots of unity, set of all p power n roots of unity. So, that is, this is set of all 1 e power 2 pi I by p power n, e power 4 pi I by p power n, and so on, e power 2 pi I into p power n minus 1 by p power n. Okay. So, this is set of all p power n roots of unity for any n greater than or equal to 1, and note that G p power n is a cyclic group, and hence it is an abelian group with Z module structure So, every abelian group is a Z module. Okay. So, it is a multiplicative group, cyclic group with respect to multiplication. Okay, with respect to multiplication. So, with the Z module structure. So, what is that Z module structure? So, for any n belongs to Z, and if I take any element x belongs to G p power n. So, n times x, it means x power n. Okay. This is our Z module structure on G p power n, it is a multiplicative group. So, therefore, it is for any n we have G p power n Z modules. So, let G take it as union of G p power n from 1 to infinity. Okay. So, we are taking G as union of this, and also note that G p is contained in G p square is contained in G p power cube is contained in, and so on. Okay. P power n roots of unity is also a p power p square roots of unity, and so on. Okay. So, because of this is an ascending chain of cyclic groups. Okay. So, we are taking G as union of this ascending chain. Okay. So, and also G is a Z module. Okay. Why? Because G is also an abelian group. Okay. Because G is an abelian group. Okay. So, it is an abelian group, therefore, it is a Z module. Okay. So, our first is G is an infinite non-cyclic group. Okay. It is an infinite group, it is clear because we have p power nth roots of unity for various values of n, for infinitely many values of n. Therefore, this is an infinite group, and it is, of course, it is not cyclic because we have p power n various roots. And the second one, it is clear, and the second one is every proper subgroup of G is finite. Okay. Every proper subgroup of G is finite. So, now let me prove this. So, let H strictly contained in G, this be a subgroup or submodule, okay, or Z submodule. It is the same structure, okay. So, that is why I will use only the word subgroup, any subgroup of G, proper subgroup of G. So, that means there exists a primitive p power nth root of unity there exists a p power nth root of unity for some n, okay, for some n not belonging to unity, say x, okay, not belonging to H. Okay. So, that is x does not belongs to H. X is a primitive p power nth root of unity. Why? Because if H contains all p power nth primitive roots of unity, then H must be equal to G. Okay. So, because if H contains primitive p power nth root, it means that it is a generator of the abelian group G p power n. Okay, because if H contains all primitive p power m roots of 1, then H must be equal to G. Okay. So, but H is a proper subgroup, therefore, one primitive subgroup at least it does not belongs to G. Now, we show that H does not contain any p power nth primitive p power nth root of p power nth roots of unity. Okay. Suppose suppose y belongs to H and y is a primitive p power nth root of unity, y is a primitive nth root of unity and y belongs to H and y is not equal to x. Okay. So, then so then x we can written as y power I for some I. Okay. Why? Because y is the generator, y is a generator of the cyclic group, y is a generator of the cyclic group G p power n. Okay. So, therefore, x equal to y power I is, this is true. So, that means that x equal to y power I, but y power I belongs to H, because y belongs to H, H is a subgroup. So, this forces that x belongs to H, a contradiction. Okay. So, therefore, H does not contain any primitive p power nth root of unity. Okay. So, and also we show that H cannot contain any primitive p power kth root of unity for any k greater than or equal to n. Okay. So, let us show this. Suppose if H contains a primitive p power kth root of unity, then our, say, let us say kth root of unity, say some z, okay, say z belongs to H, z is p power kth root of unity, then z is equal to some z power certain power a. So, this is equal to p power nth primitive p power nth root of unity a primitive p power nth root of unity. Okay. So, for some a belongs to n. Okay. So, that means that this belongs to H we are getting, which is a contradiction, right, because H does not contain any primitive p power nth root of unity, but z power a it belongs. So, therefore, which is a contradiction. So, therefore, H does not contain any primitive p power kth root of unity for any k greater than or equal to n. Okay. So, therefore, then for what really it suggests, it means that therefore, our H is entirely must be lies in G n minus G p power n minus 1. Okay. So, G is entirely sitting inside G p power n minus 1. So, but G p power n minus 1 is a finite group. So, this implies that H is finite, okay, as required. Therefore, if we take any proper subgroup of G, then that is always finite. And the third one, so the first one, so that means that first one we have shown that G is an infinite non-cyclic group and every proper subgroup of G is finite. Now, let us show third one, every finitely generated subgroup of G is proper and hence finite. Every proper subgroup is finite, we have shown. So, now show that it is finitely generated implies it is proper. Now, let us prove this. So, let H be a finitely generated subgroup of G, say generated by, say let us say Z1, Z2 and so on comma Zm. Okay. Note that each Zi has finite order, say Ri 1 less than or equal to I less than or equal to m. Okay. Why? Because these are all some p power nth roots of unity. So, therefore, each of Zi should have finite order. So, let us say this is Ri. So, then what is our H? H is just the product of powers of these Zi's. So, then H is a finite group having at most how many elements? R1 into R2 into and so on comma Rm elements. Okay. So, H is a finite group having at most R1 into R2 into and Rm number of elements. So, that means that H is finite. Okay. And H is finite and also H is a proper subgroup. Okay. So, in fact, we have shown that it is finite and hence it is proper. Okay. Okay. So, I just interchange this here. Okay. So, these are the properties that the abelian group Z what we started. So, thus G is an Artinian Z module. Okay. Why? Because G is an Artinian Z module, because if you take any descending chain of submodules or subgroups of G, if it is proper means it is finite and hence it will stationary. So, at a certain stage onwards they are equal, therefore, it is Artinian Z module. Okay. And G is, of course, G is not finitely generated. Okay. Why? Because if G is finitely generated means G should be finite, but that is not the case. Okay. So, therefore, G is not finitely generated, but G is an Artinian Z module. Okay. Okay, is it clear? So, therefore, every Artinian module need not be finitely generated. So, now let us come to one example. So, every Artinian module need not be Noetherian. So, for example, look at above group G. Okay. G is Artinian. Note that G is not Noetherian. Okay. Why it is not Noetherian? Because it is not finitely generated, since G is not finitely generated. Okay. So, therefore, G is not finitely generated, therefore, it is not Noetherian. Every Noetherian module should be finitely generated. Okay. So, therefore, this is an example of a Artinian module, but it is not a Noetherian module. Okay. So, G is Artinian. So, next remark, maximal submodules need not exist in an Artinian module. Okay. So, maximal submodules need not exist in an Artinian module. For example, above G, this is Artinian, has no maximal, G has no maximal submodules. Okay. This is one example. So, the next, a finitely generated module need not be Noetherian. Okay. If it is a Noetherian module, then we know that it is finitely generated, whereas the converse it is not true. So, let us see the example. So, let us look at the ring R is equal to, where K is a field, x1, x2 and so on, infinitely many variables. Okay. K is a field. So, let us look at this R. R is a left R module, okay, unitary left R module, whatever, okay, left R module, and R is finitely generated over R, okay, because singleton 1 is a basis, means it is a generating set. In fact, it is a free module. Okay, it is a generating set. So, therefore, it is finitely generated, but this R is not, Noetherian, because the below ascending chain is non-stationary. So, what is that? It is simply ideal generated by x1, this is strictly contained in ideal generated by x1, x2, and this is strictly contained ideal generated by x1, x2, x3. So, like this, it is infinitely, it will continue, this will never terminates. So, therefore, R is not Noetherian. Okay. So, the next one, minimal submodule need not exist in a Noetherian module, but whereas in Artinian module they exist, they do exist. For example, let us take R is equal to Z. Okay. So, this is Noetherian Z module, but and Z is not Artinian. It's clear. Okay, we have seen that Z is not Artinian. Therefore, Z has no minimal submodules. Okay, there is no minimal submodules. Next is a Noetherian module. We have seen that Artinian need not imply Noetherian. A Noetherian module need not be Artinian. For example, take Z. Okay, so Z is Noetherian but not Artinian. And also there are modules which are neither Noetherian nor Artinian. There are modules which are neither Artinian, neither Noetherian nor Artinian. For example, infinite direct sum of modules. Okay, if you take any infinite direct sum of modules, that is never Noetherian and never Artinian. Let me finish this.